In this goal, we are going to be talking about molecular motion and pressure. Kinetic molecular theory says that all matter is composed of small particles that are constantly moving and colliding, and when they collide with perfect elasticity, which means that when they collide, they don't lose any motion to friction or lose any energy to heat through their collisions. Solids and liquids will have molecules that are touching, and gas molecules are moving a lot faster than the solids and liquids, and they have a lot of empty space to travel. But even though they're so far apart, they are colliding constantly to the tune of 4 to 6 billion times per second. When a gas particle collides with its container, it exerts a pressure. A pressure is a measurement of the force and the number of collisions with the container. In class, I did a smoke rings demo. I did a YouTube video that you can watch that's similar to what I did in class. Also, I did a quick clip from a YouTube video about kinetic molecular theory. Kinetic molecular theory is an important theory. It's been around since the 1850s, and it ranks in nature of importance, just like atomic theory, that everything is composed of atoms. So let's look a little bit more about what pressure is. Pressure is measured as force per unit area, and we are familiar with the pounds per square inch. This is how our car tires and our bicycle tires are measured in pressure, even with pumping up a basketball or a football. So pounds, that's the force. In this case, it's measuring the force of gravity, and then our unit area is the square inch. And a lot of times it is represented as PSI. The scientific unit for pressure is newtons per square meter. And let me give you an example of this ballet dancer and the pressure that she exerts on the surface of the earth. So if she's just standing flat-footed, I calculated that if she weighed 100 pounds and I did just an average foot size, that the pressure that she would exert on the earth is 1.5 newtons per cubic centimeter. If she goes up on toe, we see that she exerts less of a unit area on the earth, and so we would expect the pressure to increase, and we can see that it is 50 newtons per cubic centimeter now. If she goes up on one toe, that would be half the area again, and so we would expect that the pressure would increase by double. So what does this all mean? The same force applied to a small area results in a greater pressure. So this applies to gases. If you decrease their container that they're in, the gas will exert more of a pressure. The first person to accurately measure the pressure of the atmosphere was a man by the name of Torricelli. And he was looking at some water pumps and noticing that he could only pump water up to a certain height. And past that, it was really, really difficult. The pump would pull vacuum, so it would only pump so high and then not work anymore. And so he wondered if he applied that principle to a denser material, if he could also pull vacuum, so to speak. And so he calculated with the density of mercury that he could have a tube about 30 inches tall. And so he got a tube and he filled it full of mercury and inverted it into a pool of mercury. And sure enough, he noticed that there was a correlation with the air molecules pressing down on the surface of the mercury. He said this was the atmospheric pressure, or the pressure of the air that was around the mercury. And so there's a correlation between the height of the mercury and the atmospheric pressure. And he just took his tube and he made little lines on it and measurement. And he noticed that when there was a storm come into the area, that the height of the mercury would decrease. And then when it was a clear sunny day, the height would increase. Just showing the low pressure and the high pressure that would sit over the area. So this is a barometer that he made. The height of his barometer was 760 millimeters of mercury. This is standard pressure at sea level today, and this has been around since the 1600s. You do need to know standard atmospheric pressure units, and they're right here. 760 millimeters of mercury, which is equal to a unit that we invented to make our calculations easier. So 1 atmospheric units is equal to that same amount. And also you might see pressure units represented as 760 torr, which is named after Torricelli. So notice it's the same amount as that millimeters of mercury. A unit that we use in the lab is pascals, specifically kilopascals, because pascals are so small. Pascals are the standard unit of pressure. So 101.3 kilopascals is equal to that 1 atmospheric pressure unit. And just for fun, I put in how many pounds per square inch this is. So you can kind of relate this to your car tire or your bicycle tire. So 14.7 pounds per square inch is equivalent. Now, when we look at our weather reporters on TV, what units do our weather reporters use when they're reporting what the air pressure is or the atmospheric pressure is? And the answer is they use inches of mercury. So still using the mercury scale, but we're not on metric. All right, so if you look at atmospheric pressure, so there's a difference in pressure depending on where you are. You could be here on the seashore in San Diego, or you could be up here on a mountain on Mount Everest. And there would be a difference in air pressure depending on where you were. Where would you have the highest air pressure? You would have the highest air pressure if you were at sea level. And that is because you have more air above you. So there's more collisions that are imposed on you, causing a higher atmospheric pressure. On Mount Everest, you don't have as much air above you, and so you'll have a lower atmospheric pressure. Here's another picture that shows this. So you can see that the closer you are to that sea level area, the higher the pressure. So again, standard pressure right there at sea level. Climbing Mount Everest, we see that we have a quite lower pressure of 31 kilopascals. Pressure is affected by the force of collision and what could cause collisions to be more forceful if they're moving faster. And they would move faster due to their temperature. So the higher the temperature, the higher they would be moving, the higher the force when they would slam into the container. Also, the number of particles is important. So the more particles there are, the more collisions there are. So in my first box, I only have a small amount of molecules. So this would be like when you go to your bicycle to ride it and the tires is low. So what do you do to increase the pressure of your tires? Well, you put more air in it. So you pump it up. That puts more particles, more air particles in your tire, and so you will have a higher pressure because there's more collisions. Another way to change the number of collisions is to decrease the size of your container. So if you have a container that you can manipulate, you can scrunch it smaller. And by doing this, you would cause the particles to run into the walls of the container more. So this would increase the number of collisions. So again, pressure is affected by the force of collisions and the number of collisions, and we can control that with temperature or the size of the container, or putting more or less gas in. Does the shape of the container influence the pressure of the gas? And the answer is no. As long as you have equal number of molecules in each container, you have the same volume, and also you're at the same temperature, you will have the same pressure in all these containers. So the shapes of the container doesn't matter. So in class, we did an ammonia fountain demo. So look for the YouTube link in your notes so that you can witness this and fill out your homework.